you want to choose epsilon to be maybe 10 raised to minus 5, 10 raised to minus 7, some small number. So the tolerance levels are application problem specific. Gauss-Seidel is also an iterative method, but it's an improvement over Jacobi. In the update formula, mu value equal to bi minus summation aij xj. In Jacobi, you have guessed values, those are called old here, the previous iteration. Those values are used. But in Gauss-Seidel, you make use of the fact that some x's, some unknowns, have already been updated. So old or new, depending on what is available. So you will use in Gauss-Seidel, you can use the latest values of x. Now, if you were to be solving a nonlinear system, then aij will also contain xj. In that case, aij is also evaluated with respect to the latest values of the solution again. So the small difference between Gauss-Seidel and Jacobi has a huge impact on the speed at which you converge to the final answer. So some of you may be familiar with parallel computing. In the parallel computing context, Jacobi is amenable to parallelization. Gauss-Seidel is not amenable. So if you are doing parallel computing, you may opt for Jacobi, even though it is slower. But on a sequential machine, Gauss-Seidel will give you a significant improvement over Jacobi. So in practice, both methods are used. So Gauss-Seidel is a lot more popular than Jacobi, and the difference between them is very small, a very small difference in implementation. But the differences in performance are substantial. Let's look at this example. 4, 1, 1, 4, x1, x2 equal to 5 and 5. The first question to ask is, well, in a program you have to ask, is the coefficient matrix non-singular, determinant not equal to 0? The next question is it diagonally dominant?
You can continue.
Okay, so what we will do is, after a few more slides, I will stop, and if the participants have questions, they can ask me, and then we can take it. Okay, so otherwise, just too one-sided. Okay, so all right. Now, so in this numerical example, we write for Gauss-Seidel, x1 new is 5 minus x2 old divided by 4. But now you have updated x1 already. So for x2, you can use 5 minus x1 new. So you bring in the new solution as soon as it becomes available in Gauss-Seidel. And then you can see that in the Gauss-Seidel sequence, you are approaching 1, 1 much faster than Jacobi. This will always happen. Gauss-Seidel is will always show superior performance to Jacobi. Now, if the coefficient matrix is diagonally dominant, then the number of arithmetic operations relative to the number of unknowns, capital N, matrix size is n by n. The number of arithmetic operations will be of the order of n square for Gauss-Seidel. Okay, now depending on how diagonally dominant it is, suppose it is just the diagonal matrix, then it is n. So the number of arithmetic operations in Gauss Seidel is anywhere between n and n squared. And this convergence can be further accelerated by using what is called an over relaxation factor, SOR. So here you multiply the new solution by alpha, where alpha is between 1 and 2, plus 1 minus de-emphasize the previous solution. And this will be a better estimate of the mean. And then you use the fixed Aij construct the right hand side vector Bi. Now let's discuss a linear problem. In the linear problem, Aij will not depend on the solution. So Aij can be separately constructed. Then you set up the iteration loop that x for I equal to 1 to n, and the new solution will be Bi minus summation of Aij xj, where xj is new if the new value is available, it is old if the new value is not available, all divided by Aii. So this will update xi mu. Then do a convergence check on xi mu minus xio. If it is very small, then you stop. You may also want to apply relaxation factor if your diagonal dominance is of good quality. Good diagonal dominance will mean that the diagonal terms are quite large compared to the off diagonal terms. In the nonlinear problem, the entries of the coefficient matrix A will depend on the solution. So this construction of the matrix is inside the iteration. That's the main point of reference. For the linear problem, you form Aij above equation, above that line 100. But for nonlinear problems, it will be after the line 100. Okay, and that means your CPU time also goes up. You have to form the coefficient matrix every time. Now, because you are forming the coefficient matrix every time, you also have to check for diagonal dominance. Because only if you have diagonal dominance can you embark on the Gauss-Seidel iterations. Okay, so you update xi mu as Bi minus Aij xj, mu or old. Mu if available, old if not, mu is not available, divided by Aii. And then redefine xi old after you have done a sweep over I equal to 1 to n. Redefine xi and repeat iterations till convergence. Now here I have put a remark that we will see again. In applications, you may not have to construct Aij, the full Aij. You only have to construct a row of Aij. Okay, only one row is required at any given time. If you look at this formula, you don't need the matrix Aij, you only need one row. Then you need the next row in the next sweep. So if your matrix dimensions are very large, you can save on memory by constructing one row of the coefficient matrix at a time. So essentially, when you go from a linear to a nonlinear problem, there is no major change in the program structure. Gauss-Seidel remains more or less intact. You will have the iteration loop remains indistinguishable, it remains the same. Of course, you have to ensure that diagonal dominance is available at every stage of the iterations. Of course, the advantage of not having to construct the full matrix can also be quite significant. So I think in this slide, for a nonlinear problem. Some more details are shown. 100 is commence iterations, construct Aij Bi with the previous values, the guessed values of the solution. Check for diagonal dominance. And then apply the Gauss-Seidel update formula for every I. So one comment is you need only one row of the matrix at a time. The other comment is while solving the differential equations, I equal to 1 and n may be boundary conditions. So this equation has to be applied only in the interior of the domain. So I actually will go from 2 to n minus 1. It's another matter of detail. And then convergence criteria, you may look at the new minus old absolute value, maximum over all I less than epsilon 1, or the root mean square value can be less than epsilon 2, or ax minus b modulus. Because after all, you want to satisfy the equation ax equal to b, therefore ax minus b should be 0. So you look for ax minus b modulus to be less than epsilon 3. These are convergence criteria that can be used along with Gauss-Seidel iterations. Okay, so now before I start looking at some differential equations, I'm going to Satyendra.
Yes, sir. Hello, sir.
Yeah, I'm going to stop for a minute.
Okay, sir.
And if there are questions, you can ask me. You can unmute yourself, ask me, or send me on chat.
Okay. So I'm requesting to participants. There is going a very short question and answer session. So if you have any queries related to the lectures which we have covered till the moment, so you can raise the question to our experts. Professor Kevin.
Dr. Ashok Mishra here. Yeah, Dr. Ashok Mishra here, sir. Good morning.
Yeah.
Sir, please, can you please explain what is the difference in linear and nonlinear systems?
Yeah, that's a good point. If you have governing equation is ax equal to b.
Yeah, ax equal to b.
Now, if the entries of A are all constants independent of the solution x, that equation is called linear. But if the entries of the coefficient matrix depend on x, the solution itself, then that equation ax equal to b is said to be nonlinear, because if you expand, then you're going to multiply x by, let us say, itself, or square root of x. You're going to multiply x and square root of x. Square root of x may appear through the coefficient matrix. Then it will become x to the power of 3 over 2. So you lose linearity in that case. So that may happen if your differential equation is nonlinear. Let us say you have temperature-dependent thermal conductivity. Then the discrete form will have coefficients that depend on temperature. But you don't know temperature. So in that case, you will have to guess the solution, construct the coefficients, then solve the linear problem, and then update the coefficients and repeat. Okay. So essentially, linear and nonlinear are with respect to the here in the present discussion, it is ax equal to b. The entries of A are all given to you, that makes it a linear system. But if the entries depend on x, it's a non-linear system.
Depend on the variables. Depends on the variables.
Yeah, if they depend on the unknown itself.
Unknown itself, okay.
Yeah, so I think there are one or two examples in the subsequent slides. Yeah, next, yeah.
Yeah.
Hello.
Yeah.
Hello. Good morning, sir.
Yeah.
So my name is Bharat Singh Negi. So I wanted to ask that suppose we have a set of equations and we want to solve them using the matrix method. So, sir, you said this diagonal dominance. So, do we have to convert it to diagonal dominance form to check whether it is performing or it is already converted?
Yeah, so in some examples to follow, we will see just by inspection, we will know that the coefficient matrix is diagonally dominant. In some cases, just by inspection, you will know that it is not diagonally dominant. So,
Okay, sir.
but then in good computer programs, you will include a check for whether the matrix is diagonally dominant, and then you can also put in what is called a pivoting strategy. Pivoting is a process of exchanging
Exchanging the
rows and columns of a matrix till finally you have a diagonally dominant system. Not every matrix will end up as diagonally dominant. So all this exercise can be done separately even before you have started solving them. You can include the check in your main computer program, but this is called a pre-analysis of your solver. Even before you have applied Gauss cycle, separately you can check is the coefficient matrix. Well, you have to start with the determinant. Is it singular, non-singular? Is it later we will study conditioning? Is it well conditioned or is it ill conditioned? Is it diagonally dominant or not diagonally dominant? All these questions can be asked separately. Even before you start solving Ax equal to B for x.
Yes, sir. Thank you, sir.
Hello, excuse me, sir. Good morning, sir. Sir, I Nirmal Kumar, sir. Sir, I have some questions, sir. Sir, in which factor parallel computing is done, sir?
See, I told you that the number of unknowns in a problem, in a so-called real life problem, okay? Everything from engine simulation to flow over an aircraft, even flow over an automobile. The number of unknowns can run into millions, if not billions. Okay, now if you are trying to solve, and then it's a non-linear system, then it is time marching. So you will have a huge computational problem at hand. And each run may take maybe a few weeks or maybe a few months of CPU time. If you are in that situation, your big question is how do I reduce CPU time?
Yeah.
So one possibility is you try running. See this operator x nu equal to bi minus aij xg divided by aii has to be applied to every node I. So if you are working with, let us say, nodes I equal to 1 to 100, you may have 10,000 nodes. Let us say you are doing I equal to 1 to 100 on one processor, and you may be doing 9,000 to 9,100 on some other processor. You can implement this formula jointly on many processors. So you don't have to wait for all the calculations to be over. Jointly, in parallel, you are carrying out these calculations that may end up reducing your CPU time. So parallel computing is a multi-processor operation in which the core of your algorithm is run on multiple processors, and as a result, you gain CPU time. The total time that you have to wait for is the initial time on a single processor divided by number of processors. Almost a percent.
And sir, there is another method better than parallel computing.
Well, I think parallel computing is also not the best. I mean, it's one of the methods available for reducing the CPU time. See, I don't want to say that every big problem can be reduced into a small problem. A big problem is a big problem. Okay. But purely from the viewpoint of CPU time, you may be able to cut down on the computational time. In some cases, by using some strategies like parallel computing.
Okay, thank you.
Okay, sir. I have a question. Actually, there is a participant, Anupam Chaube. He has messaged that due to some issue related to microphone, he is not able to question to you directly. So he is requesting. So I am asking on the behalf of Anupam.
I should be able to see his chat.
Yes, sir. Then you can answer, sir, directly to Anupam Chaube.
Yeah, I'm just trying to see chat. What is his name?
Anupam
Anupam
Chaube.
Chaube, yeah. What is meant by well-conditioned, ill-conditioned? So, that we will cover a little later, but we have already seen that if the matrix is strongly diagonally dominant, then it means that all the information is clustered around the main diagonal, in which case you can get the solution quickly. If all the information, for example, if you have just a diagonal matrix, then all the information is on the diagonal. Then the solution is simply right hand side divided by the diagonal entry. So a matrix that is easily invertible, or is the system that is easily solvable, is said to be well conditioned. It's easy to solve. A system that is not easy to solve is said to be ill conditioned. Okay, now we will look at a more specific definition later. But for the time being, I think this definition should be all right. Okay.
Excuse me, sir. Sir, Nirmal Kumar, sir. Sir, I have one question more, sir. In your PPT, you written that in a computer program, tolerance level for convergence can be as small as 10 to the power minus 10. It means?
Yeah, see, it's like this. In a hand calculation, you cannot carry such small numbers with you. But in the computer program, the computer carries numbers as small as 10 raised to minus 30, for example, or even minus 60. So it all depends on the computer available to you. So these are automatically small numbers that are carried by the computer. So you can converge, you are looking for the difference between left-hand side and right-hand side. Let us say ax minus b. You want it to become smaller and smaller and smaller. So you want to see how small it's going to become. You are not satisfied with 10 raised to minus 3. You can keep making it smaller and smaller. This you can do only in a computer program because the computer will carry such small numbers with it in its memory. So you can make it minus 10, minus 15, minus 20. You keep looking at the solution ax minus b. And you are iterating. As you improve or as you keep iterating, as you increase the number of iterations, ax will become closer and closer and closer to b. So the difference will approach 0. It will never become 0 because there is always some round off. But it can be easily 10 raised to minus 10.
It means, sir, it will give a good result.
Correct, yeah, that's correct. If ax minus b becomes 10 raised to minus 10 or 10 raised to minus 20, then ax minus b is approaching 0.
Okay.
So that solution is better than the one with, let us say, ax minus b equal to 0.1.
Okay, sir.
Okay, is there anyone else? Hello, is there anyone?
So let me continue now. Huh?
Yes, sir. Now you can continue, sir.
Yeah.
Okay, thank you, sir.
Yeah, so I was here. So let's, so we can ask, do we get diagonally dominant matrices in CFD? Okay, that's the question. So to keep the discussion inside one slide, I took this example, d to t dx square equal to 0. With left-hand side, boundary condition is 1. Right-hand side, boundary condition is 0. This is like a slab problem. The analytical solution is a linear variation in temperature 1 minus x. We set up a grid, I plus 1, I minus 1, where I goes from 1 to n. And discretize d to t dx square equal to 0 by, let us say, finite differencing. You have several methods of discretization available. But let's say we have done finite differencing. And it will give rise to the equation ti plus 1 minus 2ti plus ti minus 1 equal to 0. Now I depends on I plus 1, I plus 1 will depend on I plus 2 and so on. So you have a system of coupled algebraic equations. And if you write it in matrix notation, you see that the coefficient matrix does not have any dependence on the solution. So they're all constants. So it's a linear system. It's a linear system of algebraic equations, which will happen if your governing equation d to d dx square were to be linear. If the differential equation is linear, discrete form will also be linear. Now this matrix you can see is tridiagonal. There's 3 diagonals. And it also has diagonal dominance because diagonal term is greater than equal to sum of the off-diagonal terms. And if you look at the first row and the last row, you have strict diagonal dominance. So here you can use Gauss-Seidel method and then iteratively obtain the solution. By the way, if you have diagonal dominance, neither the solution nor the convergence pattern will depend on the initial guess. It will converge for any initial guess. That's the implication. So it's a very strong result. If you have diagonal dominance, the solution is independent of the initial guess, and the convergence rate is also independent of the initial guess. So we said something like n square operations. So in n square operations, you will get the solution. So here is an example where indeed we get diagonal dominance. And of course, we notice that iterations have to be done for the interior nodes, node 2 all the way to n minus 1, because boundaries are at fixed temperatures. You already know the solution at T1 and Tn. Let's look at another example where d to d dx square is 0, but the boundary conditions are the first derivative, dt dx is 0 at x equal to 0 and L. Now, if you discretize the boundary condition, you will get minus 1 and 1. That means t2 minus t1 is equal to 0, tn minus 1 is equal to 0. Now, is this matrix diagonally dominant? No, because you don't have any row where you have strict diagonal dominance. All of them are only weak diagonal dominance. So this coefficient matrix is not diagonally dominant and it cannot be solved by Gauss-Seidel. In fact, you can show that this coefficient matrix is singular. The determinant of this matrix is 0, and you do not have a you don't know if you have a unique solution. You don't know if there is a solution. You don't know if there is a unique solution. But one can show that there is a solution, but it is not unique. T equal to any constant is a solution of this problem. So here is a counter example. So you have to pick your boundary conditions carefully so that you have a non-singular system before you start solving. So somebody asked, should I check for it? The answer is yes. You have to check. You have to do some pre-analysis before implementing the solver. Is the system diagonally dominant? Is the system non-singular? All these checks have to be done beforehand. Here is an example where the system is singular. So you cannot apply Gauss-Seidel. So you should not run the Gauss-Seidel program for this matrix. This is a fin problem. d2t dx squared minus 4t equal to some right hand side, and then base temperature is 0 and tip temperature is 1, and the solution, analytical solution, has this hyperbolic form. Discretizing, you see that the diagonal term has now become minus 2 minus 4 delta x squared, which is greater than 1 plus 1, the off diagonal terms. So here the coefficient matrix, is it linear or non-linear? It is linear because it does not depend on temperature. But it is strongly diagonally dominant. So the Gauss-Seidel method will definitely apply. And in fact, you should use over relaxation here, and then you will get further acceleration in convergence. So this fin problem is amenable to Gauss-Seidel iterations because it gives rise to a very strongly diagonally dominant matrix. I'll skip this slide. These are some intermediate slides that I think the question was, how do you pick the initial guess? Now, one comment is it does not depend on the convergence, nor the solution depends on the initial guess, but you still have to pick an initial guess. One could be set temperature equal to 0 everywhere, or set temperature equal to 1 everywhere, or set temperature equal to a linear variation from 0 to 1 everywhere. All these possibilities are there. Or you can just set the solution of the equivalent diagonal matrix as your initial guess. That means you suppress the 1 on the off diagonal term to 0. Then the right hand side will be bi divided by dii, which is minus 2 minus 4 delta x squared. That can be taken as the initial guess. So there are several ways. In this slide, the solution of a similar problem, d2t dx squared equal to 0, has been chosen as the initial guess. You can demonstrate that the convergence rate and the solution will not depend on your choice. And here I'm also showing you an extra detail. The detail is, see, for T1 and T5, these are boundary nodes, these are fixed. So there is no superscript new or old for them. And then as you go along, when you do T3, T2 has been solved for already, so you can use the latest value of T2. But T4 is yet to be obtained, that will be the guessed value. So use new and old will have to be judiciously used. So this is a matter of detail. Let's look at counter example. Suppose d2 dt x squared plus 4t is equal to 0, then the diagonal term will be minus of 2 minus 4 delta x squared. So this is not diagonally dominant. So here you cannot use Gauss cycle. Other methods may be used, but Gauss cycle cannot be used. Okay, why? Because you do not have diagonal dominance. Okay. Now let's look at a slightly more difficult example. It's the unsteady diffusion equation. And when you discretize it, you will have temperature a function of the index I. Index I is in the space domain, and the superscript n is in the time domain, in the vertical direction, I and n. So you have Pi n plus 1 minus Ti n over delta t. This is the time discretization. It's called FTCS, forward in time, central in space. I have shown the implicit version, that means the right hand side is evaluated at the new time level n plus 1. So if you express it in matrix notation, I think somebody has to mute his audio. Satyendra?
Yes, sir.
Yeah, I think that there is some background noise. So
There is some background noise. Participants,
they have to mute their audio.
mute your mic. There is some sound coming in the background.
Yeah.
Sir, can you check?
Okay, so let's continue. So suppose you had used an explicit method. Notice that there is no matrix construction required for finding this Tin plus 1. The basic unknown is Tin plus 1. It is available to you in terms of temperatures at level n. So explicit methods will not require you to form a matrix. So that is a big advantage. But then you also know that explicit methods have a stability constraint. They require you to use very small values of delta t. Implicit methods will not have a time step restriction, but they will require you to form a matrix, like in the second equation, Tin plus 1, I think it's given down below. Tin plus 1 depends on Ti plus 1 n plus 1 and Ti minus 1 n plus 1. So the coefficient matrix has this form. R is the great Fourier number, alpha delta x square.
नहीं नहीं तुम फ्राइड राइस बताओ मैं देख लूंगा क्या करना है.
Okay, so is this coefficient matrix diagonally dominant? The answer is yes. It is very strongly diagonally dominant because there is this 1, extra 1 on the diagonal term. So it is 1 plus 2r, while the off-diagonal terms add up to 2r. So in a unsteady formulation, you get a coefficient matrix which is strongly diagonally dominant. In steady state, that 1 was not there. So unsteady gives you a matrix which is more strongly diagonally dominant than the steady state formulation. So you might see in many commercial solvers in research papers that they always start with the unsteady problem and march in time. So till you reach steady state. That approach is preferable because the coefficient matrix is strongly diagonally dominant and Gauss cycle will apply. Plus, you also have a good idea of the initial guess. The solution at the previous time step is a good initial guess, so you will reach convergence very quickly. So here on the left hand side we compare the coefficient matrix steady formulation. The terms are 1 minus 2 1. Okay, so on the right hand side the diagonal terms are, the interior terms are r minus 1 plus 2r and r. So this unsteady is strongly diagonally dominant and steady state will give you diagonally dominant. So even if you want to solve d to t dx square equal to 0, it's preferable to solve del t del time equal to alpha del 2t del x square and then march in time till you get the steady state answer. The other comment is, suppose you had pure Neumann conditions on the two sides, you still have diagonal dominance in the interior. So even for the pure Neumann problem, unsteady formulation can be used and you can get the steady state solution. Okay, here let me introduce at the end of the slide, you will see the nonlinear diffusion equation where thermal conductivity depends on temperature. So when you discretize this equation, you can expect the matrix entries to contain K and therefore the matrix entries will depend on temperature. That's a nonlinear problem. So like here, we discretize, this is the governing equation V dx K dt dx equal to some right hand side. Thermal conductivity can be a function of temperature. Then when you discretize on this grid, small e and small w are midpoints of I and I plus 1, I and I minus 1 respectively. The discrete form has conductivities. Conductivities depend on temperature. Therefore, the coefficient matrix has entries that depend on temperature. So you have a nonlinear form. Now, Gauss-Seidel will work here also. It does not depend on whether the matrix is linear or non-linear. It just needs a diagonally dominant system. So here we write Ti new equal to K east, Ti plus 1 old, Kw Ti minus 1 new. Why new? Because by the time you have reached the ith node, I minus 1 has already been processed. So you have the latest information. And that latest information can go into Kw also. So this is a diagonally dominant system because you have K east and K west in the denominator. And then you can use the same Gauss-Seidel routine that you had for a linear problem. Except that these coefficients have to be calculated inside the iteration loop. I'll just pass a small comment that in practice, if you want to find a quantity like K small east, you can either find K at the average temperature T small east, or you can use harmonic averaging. Okay, I and I plus 1. So this harmonic averaging is usually preferred in CFD. I don't think I have the time to discuss it, just small comment. But the next slide explains why harmonic average is preferred. But you can look at it separately. So we have reviewed we have gone through Gauss-Seidel, both linear, non-linear versions. I'm providing you with a small computer program in case you want to write your own program. This is a program for Gauss-Seidel. So let's see what is the time. So it's 11 o'clock now. We have quite a few slides to complete, so try using this computer program. The main update formula is in the middle, str. The dependent variable is str. I had string function in mind. It's written as right-hand side minus summation of all the off-diagonal terms divided by the diagonal term Cii. Coefficient matrix is C. So this is the update formula, followed by convergence limits and then iterations. Let's take a look at a 2D problem. So it's a square region and the grid has I index and j index for x and y and n index for time, I, j and n. So we have Tijn plus 1 minus Tijn divided by delta t is equal to right hand side evaluated at n plus 1. That is the implicit formulation. East, west, north, south, that's the notation used for representing the neighborhood of point P. This is a kind of a normalized equation. I'm not showing alpha in the governing equation. So the grid Fourier number is delta t over delta x squared in dimensionless form, giving rise to the Gauss-Seidel formula. T at point P n plus 1 is equal to r times east, west, north and south summed up plus Tp at n divided by 1 plus 4r. So this is a strongly diagonally dominant because the off-diagonal terms add up to 4r, but the diagonal term is 1 plus 4r. Because of this 1, you have extra diagonal dominance. This is the Gauss-Seidel update formula. At this point that you do not have to construct a matrix. That is to be highlighted. We are doing it for a point by point. Each point P, you apply this formula. So there is no formation of a coefficient matrix. This matrix, this formula is also called the successive substitution formula. So it's based on Gauss-Seidel iterations. There is no coefficient matrix being formed, and it has strong diagonal dominance. If you were to do a steady state calculation, then you take the same formulation and march in time till you reach steady state. Just for generality, I have shown initial conditions above. Along with the governing equation, you have initial conditions that can depend on space. Then the boundary conditions can depend on time. Now, if you have to solve this problem analytically, it may require you maybe 8 to 10 pages before you get the closed form solution. But numerically, in a program that is not more than 2 pages long, you can get the numerical solution of this problem. Now, the consequence of strong diagonal dominance is you can use over relaxation and accelerate convergence. So here is a computer program. So I think these numerical methods become clear only when you write your own program. That's why I'm encouraging you to either adopt this program or write one on your own. So here is the domain for this particular computer program. Left boundary is at temperature 1, all other boundaries are 0, initial condition is 0. And the domain size is 1 by 1. So initially, you have to specify the guessed temperature. Then the initial condition is T old is the initial condition, and dumb is a reference variable that you use for checking convergence. So T minus dumb inside an iteration loop should become small. Then 500 is the overall time marching loop. Okay, so when you go from n to n plus 1, that's indicated by the 500 loop, and inside that you have iterations given by the 600 loop. Inside that you have boundary conditions. These boundary conditions can be placed outside the iterations also. So at the top you have the successive main Gauss-Seidel iteration formula is Tij equal to A east T east. I plus 1 J is temperature at east. A east is the coefficient of the east temperature plus A west T west. That was shown to be R in the previous discussion. North times temperature north, A south times temperature south, plus A old times the previous temperature at the previous time level, time instant divided by the diagonal term AP. The diagonal term is 4, which is A east plus A west plus A north plus A south plus the factor corresponding to the grid Fourier number. And then this 100 will do the sweep across all values of I and all values of J. Then you check for convergence. If there is no convergence, then you go back to 600 and do the sweep over all nodes. If it has converged, you go out, then update the old with the new in terms of time step and continue the time step. So the structure is an outer loop for time, an inner loop for iterations, and inside that you have an I and J sweep. This is the program structure. Okay, so if the boundary conditions were to be strictly constant, they could be outside all these three loops. But if you are writing the general purpose program, you put them inside so that you can make them, boundary conditions can be made functions of time. Try out this computer program. So if you have a nonlinear system, we looked earlier, we checked earlier the nonlinear steady state problem. Here we have a nonlinear unsteady problem. There is really no change in the program structure or the algorithm structure. So here you have K east, K west, T west at the new time level, n plus 1. Where K east is to be found as the harmonic average of I and I plus 1. K west is the harmonic average of conductivities at I and I minus 1. Okay. Small east and small west are between I and I plus 1, I and I minus 1, respectively. So linear, non-linear, you can use the same tool, same technique. Now, analytically, if you try to solve this problem, I don't think there is a solution to this non-linear analytical PDE. But numerically, without too much of an effort, you can get the solution. In fact, the computer program of the previous slide, the linear version, can be easily generalized for non-linear. So here you have to make conductivity a function of temperature. It gets into the calculation loop. And these coefficients, instead of being 1, are now the conductivities, and you have to use harmonic average. These are some additional considerations. So in this manner, I'm encouraging you to look at a diffusion reaction equation. Let's say reaction term Q depends on temperature. Invariably, this Q is heat generation, it will decrease with increasing temperature. Now, what will be the effect of this Q on diagonal dominance? I will leave it to you to show that the reaction term will strengthen diagonal dominance. So Gauss-Seidel can be used here also. Similarly, radioactive decay will also strengthen diagonal dominance. So you can use Gauss-Seidel in this problem as well. What about treatment of a semi-infinite solid? Well, here you don't have any shortcut. You have to solve on a region 0 less than x less than capital L, and then keep repeating the solution with increasing values of L. Usually your interest will be in the solution close to x equal to 0. So you look for convergence in the solution close to x equal to 0 for increasing values of the slab thickness. You cannot put infinity straight into the computer program, because that will make delta x, which is slab thickness divided by n minus 1, where n is the number of nodes. But slab thickness becomes infinity, therefore the grid size becomes infinity. So you cannot work with infinity in the computer program, but you have to do a sequence of calculations that will have a limiting value close to x equal to 0. Okay, so now again I will take a small break from Gauss-Seidel was an iterative method for solving the system of equations. We start a new discussion on non-iterative techniques. So before that, I'll go here. If you have any questions, please let me know, either on chat or you can ask me some questions directly.
Sir, good afternoon. I'm Dr. Ashok Mishra.
Yeah, please.
Yeah, sir. I have 4 doubts. First one is, sir, how to choose the initial guess for Gauss-Seidel or Gauss-Jacobi? We are doing.
Okay, if your system, the answer is simple. If your system is diagonally dominant, then the solution does not depend on the initial guess. So it means any initial guess can be used. Okay, you may set t equal to constant, or you may set t equal to some linear variation, and then so that can be your initial guess. But then you can also use the solution of the equivalent diagonalized problem. You assume that your coefficient matrix is just the diagonal form. Okay, all the off-diagonal terms are 0. Then you can solve that system and you will get t equal to right-hand side divided by diagonal. That can be your initial guess. So essentially, initial guess is the solution of a similar problem.
Okay. And sir,
Okay,
we
next.
are using FTCS, means forward difference for the time zone and central difference for the space zone. We are considering. So FTCS, or you can say forward difference or backward difference also is there. We are unable to understand, sir, for which problem, which kind of finite difference technique will you use? Is there any standard rule for that?
Okay, if you use backward in time, backward in time is used if you are marching backwards in time. That means you have the solution at some time t and you want to go back in time, then the solution at time instant t becomes the initial condition. Suppose you have an initial condition at time t equal to 0. then you cannot use backward differencing because you don't have any information on n minus 1.
Okay.
So you have to use n plus 1. You can only use forward in time.
Okay.
Okay. Then central differencing is better than one-sided differencing because it has errors of the order of delta x square. If you use forward or backward, the error will be of order delta x. Delta x is small, so delta x is a small quantity, therefore delta x square is a very small quantity. So central differencing is a better approach than one-sided differencing. So in balance, in general, FTCS is like a general purpose approach to solving differential equations.
Why do you use central difference for the space domain? Because of that delta x.
Because it gives you higher order discretization error. So the error will be of order delta x square. If you use central differencing, discretization error is order delta x square, which is much better than order delta x if you were to use first order techniques.
Okay. So it is better, FTCS is better actually.
FTCS is like a good balance between among
okay.
all there are hundreds of methods available. It's like it's a good average approach.
Okay. And my third question is, sir, when we are discussing this partial differential equations, either linear, non-linear, we should go for parabolic, hyperbolic, elliptic equations. So any type of equation, can we go for this Gauss GS method, Gauss-Seidel method, or it has an impact with respect to parabolic, hyperbolic, elliptic?
The point is, if you can construct a diagonally dominant matrix, then Gauss-Seidel will hold, irrespective of the type of differential equation you are working with.
Oh, if it's diagonal dominant, then any kind of equation also we can solve. There is no problem.
Correct. Right. Yeah. So it depends. Yeah. So the only requirement is it should be diagonally dominant.
Okay.
Okay. Now, if you have a hyperbolic system, then there are methods that will give you high accuracy even without forming a coefficient matrix. Okay, so you don't see matrix construction that often in hyperbolic systems.
Okay.
So generally the discussion is restricted to elliptic or parabolic. Hyperbolic, there are other methods that will give you a solution without forming a coefficient matrix. But you can also form a coefficient matrix. So if it is diagonally dominant, Gauss-Seidel can be used. Whatever be your governing equation. Yeah.
Okay, sir. And my last question is, sir, generally CFD we are using FDM or FBM methods, and FEM generally we use solid geometry, solid structure actually. Now the question is, as compared to FBM, FDM is a little bit easier to apply. But why do people prefer FBM instead of FDM?
That's a good point. Finite volume method has some geometric flexibility. You can do complex geometry problems somewhat more readily than using finite differences. That is the only advantage you have in finite volume.
Finite difference you cannot use there.
Finite difference, it's a little more complicated. You have to see, by and large, finite difference will hold if you have a circular region or a square region or a rectangular region. If you have an elliptical region, then you will have to transform elliptical into circular, and then you have to use some coordinate transformation approach, and then use finite difference. So it's a somewhat longer approach. But you can use the original governing equations and discretize using finite volume, even if the geometry is complex.
That means FBM method can be used to used in any case. There is no problem actually.
Correct.
Complex
Finite
and simple
volume,
both.
complex and simple both.
Okay, but FDM is difficult for the geometry.
For the complex geometry, right?
But it is possible.
Yeah, what is easy? No, but it is possible. Many people prefer to use finite differences even for complex geometries. Now that
Yes,
is there is a small group, but for some reason, finite volume has become popular over time. More and more people are, mainly because these commercial solvers also use finite volume.
Sir.
Because they want flexibility with respect to geometry. So that's the reason why finite volume has become very popular. But there are many individuals using finite differences